Good morning and welcome to this webinar on an introduction to OptumG2. My name is Christian Gravenhoft. I'm from Optum Computational Engineering. This presentation, I have a brief outline of it here. This webinar will give a brief introduction to the program OptumG2, focusing on our analysis capabilities, and especially some of the analysis capabilities that are unique to OptumG2. First and foremost, limit analysis, and in connection with that, automatic adaptive mesh refinement. I'll say a few words about what we have of available material models as well, and then I'll move on to three applications: a shallow foundation, an example of slope stability, and an excavation, a staged excavation example. First of all, what is OptumG2? Well, OptumG2 is a finite element program for geotechnical applications. It's 2D, the G stands for geotechnical, the 2 stands for 2D. It is a general purpose finite element program geared at geotechnical applications, but it's finite elements with a twist. And if I was to say the one thing that probably distinguishes the program OptumG2 from other similar programs available on the market, it is that it really provides the ability to provide direct answers to direct questions. And what I mean by that is that as users of finite element software, you often have a very concrete and a very direct question, such as what is the bearing capacity of my foundation? Now, with conventional finite element analysis, you would answer these kinds of questions in a rather indirect manner. You would, for example, to determine the bearing capacity, do a full load displacement analysis step by step up until failure. That can be done, of course. It's kind of tedious to do. It is not without complications either. Frequent numerical problems are encountered and so forth. Whereas with OptumG2, we have an analysis type directly geared at answering this question, and that is, in this case, limit analysis, which in one direct calculation gives a very direct answer to a very direct question. There's lots of examples like this, and I'll go through some of them in the examples, in the application examples in a little while as well. So this really provides a very high level of user friendliness, just this ability to answer direct questions in a direct manner. That's one aspect of user friendliness. Another aspect is, of course, the graphical user interface that we have paid a lot of attention to in terms of trying to come up with a good way of sequencing operations, for example, in connection with staged excavation. And we have a lot of useful and convenient features embedded in the graphical user interface. I'll show, of course, examples of that later on as well. And then the last aspect of user friendliness is really the calculation core, which is extremely robust. That's something I think that's often overlooked in finite element software. The robustness of the calculation core is really central to user friendliness. You really don't want to be spending any more time than you absolutely have to with playing around with parameters, sometimes algorithmic parameters, sometimes material parameters, and in many cases parameters you don't really know what they represent, in order just to get a reasonable solution. So the robustness we have in OptumG2 completely avoids that and gives really reliable answers, regardless of the difficulty of the model. So I'll have examples of that a little bit later on. So something that I think is well recognized in geotechnics: materials with zero cohesion and very high friction angles, so sands, very common material, are very difficult to handle. In OptumG2, they are handled with the same ease as any other material. So this robustness gives a really high level of user friendliness as well. So some of the analysis capabilities are listed here, starting with limit analysis, and that is really a fast and rigorous means of evaluating the bearing capacity of geostructures, foundations, slopes, and so on. And not only coming up with an approximate solution as we're used to with any other method, but actually coming up with an upper bound and a lower bound. so that you know the true solution is somewhere in between. So we don't only calculate one approximate value of the bearing capacity, but an upper bound and a lower bound, a conservative and an unconservative solution. Strength reduction, same kind of thing. Here you reduce the material parameters to have an expression for the factor of safety, and not only one value, one approximate value of the factor of safety, but an upper bound and a lower bound as well. Elastoplastic analysis, that's more in the sort of the conventional domain of finite element analysis. We have implemented in a slightly different way, but it's the same physics, it's the same mathematics at the end of the day. That's for deformation, settlement analysis, of course. Seepage analysis, we have a general variably saturated formulation for that. Consolidation, initial stress analysis is a sort of a unique approach as well, available only in this program for calculating the in situ stresses in the ground, so the initial stresses in the ground given the earth pressure at rest coefficient K0. And then stage construction, which is not an analysis type in itself, but comes about by linking elastoplastic and consolidation and various other stages. I have examples of that as well a little bit later on. Special features, and they're not all that special, but just to say, with regard to structural elements, we have all the elements you need for the modeling of walls, anchors, geotextiles, so forth. Shear joints for modeling interfaces, cracks, joints, that's especially, I think, useful in rock mechanics applications, where it's being used a lot. Adaptive remeshing, again, examples will follow surely that will sort of illustrate what this is all about, but it's basically, the idea is to put the elements where the action is, and in that way you can really minimize the computational time while at the same time maximizing the accuracy of your solution. Automatic seepage analysis, just to say that seepage is carried out as part of any mechanical analysis, if relevant. So you don't have to do the seepage analysis in one part of the program and then import the pore pressures into another part of the program to do the mechanical analysis. It's all embedded. Materials library, so we have a good selection of materials, and then design approaches. See, the whole philosophy of OptumG2 is very much in line with the philosophy of Eurocode 7, the new geotechnical standard that's mandatory throughout Europe. And the limit analysis is a big part of that. And then in addition to that, we have some inbuilt functionality that allows the partial factors to be applied very conveniently, the partial factors according to one of the three design approaches of Eurocode 7. Soil and rock models from the classical, more Coulomb, Drucker-Prager, Tresca, to the more advanced Hook-Brown, again, I think the state-of-the-art model for fractured rock masses, modified CAM clay. It's really, we should use another name for that, but it's a very much extended and enhanced version of that classical model for soft soils. The hardening more Coulomb model for more hardening soils. If any of you know the hardening soil model, this is very similar. And then various other models, Bolton, incorporating a model incorporating Bolton stress dilatancy relations for sands. So basically, you have an increase in strength at low confining pressures. That's what Bolton, that model accounts for. And then the anisotropic undrained shear strength model meant for very soft sediments of the kind you find offshore usually. Typical applications, that's all the typical applications you can think of in geotechnics, slope stability foundations, retaining systems, excavations, and so forth. And I have a few of them coming up right now. The first one, a strip footing on clay, a very classical example. And if you were to design a footing like this, you would need to do it depending a little bit on where you are in the world, but usually it would be done, you would have to say something about the ultimate limit state and then the serviceability limit state. So you need to determine the bearing capacity and then you would need to determine the settlements under the working loads. And I'll go through this example with OptumG2, so I'll start up the program and set up this problem. So when you start the program, I should say, to start with, you're greeted by this welcome window where you have some of my recent projects are over here. All the manuals in PDF format that come with the program, I can open those from here. There's the examples manual, which contains quite a comprehensive list of examples, 50 in all, covering all kinds of problems from bearing capacity, foundation, slope stability, sea pitch, retaining walls, rock mechanics applications, and so forth. And all the examples described in the manual, the input files to those come with the programs. They are listed over here. So that's a useful way of getting started, I think. So then just a few words about the organization of the GUI, the graphical user interface. So we have the canvas, as we call it, the drawing canvas, the dark area here. And then we have the ribbon, and the ribbon contains 4 tabs. First, geometry, where we have tools for defining and manipulating geometry. Then materials, where all the materials are listed. Features, which is all about supports, loads, structural elements, anchors, and so forth. And then finally results, which will be populated once results are available. But to get back to the foundation, yeah, and then over here on the right hand side, of course, we have the so-called stage manager, which I'll get to in a minute, where the different analysis types are defined, where the number of elements is set, and so forth. So, but to get back to the foundation, I will then use the rectangle tool to create a rectangle. That's my soil domain, and then put a footing on top. That's another rectangle. I won't worry too much about the dimensions here, just for this simple demonstration. Then I have the geometry defined, and one of the key ideas of the user interface is that if you want information about anything you see on the screen, then you select that entity with the mouse. So for example, a point here, well, the information that's available comes up over here. That's the point number, which is not really useful for anything. And then the coordinates that you would then be able to change, okay, if you want. So that is quite convenient as well. So we don't have this system this menu system where you have a menu and then you enter into a sub menu and a sub menu, and you get deeper and deeper into the sort of a directory tree. Everything is on the surface. So that's geometry. Materials, and again, the materials are listed up here. What we need for this footing is we want to do a Tresca analysis, so an undrained analysis with a given undrained shear strength, CU or SU. And as I said, what is Tresca? This material Tresca Basic all about. You click it and the information comes up over here in the property window. We have an EU, an undrained Young's modulus, and a CU, undrained shear strength. We have the possibility to apply a tension cutoff. I won't do that here, but it can be done. Unit weights, something with the initial state, the earth pressure coefficient, and then something with the hydraulic model, which we're not going to use in this example. But to apply the Tresca material to the soil, I can drag and drop it, or another way of assigning materials to domains is to select the domain and then select the material. And here I've selected a rigid material, which is a perfectly rigid material that I'll use to model the footing. So that's geometry and materials. Then to features, and we need to apply boundary conditions. First of all, supports. For those of you who know Plaxis, you probably know the standard fixities button. We have an identical button which applies normal supports here to the vertical edges and fixes the bottom edge here fully. And then we need to apply some load to the foundation, and I'm going to consider the problem of bearing capacity to start with. So what we want to do here is we want to apply a so-called multiplier load. That's a load which has a magnitude of, so in general a linear varying load. It's uniform and has a magnitude, in this case it's uniform and has a magnitude of 1 or minus 1 at both ends. And the question is then, by what factor, can I multiply this load, can I amplify this load before I reach failure? That's basically what limit analysis is all about. So if we go over to the stage manager, all the analysis types are listed here. In this case, limit analysis is the default analysis type, so I'm happy with that. And then for each stage, we have only one here, but for that stage, there are various settings down here. There's the number of elements, 100 by default. I'll change that to 1000. And then the element type. So lower gives lower bounds on the bearing capacity, upper bounds, and then we have various other elements which give something in between. But let's try to do a lower bound limit analysis first. So that's all set up with this stage. Now what I'm going to do before I actually run the analysis, I'm going to clone this stage, so create a copy of it, and then I will change the element type to upper. So now I have two identical stages, except that one has element type lower, the other one has element type upper. Let's say LB and UB for upper and lower bound. And then I'm ready to run the analysis, and I click the run analysis, the play button if you like, and the results come up on the screen here. That's for the first stage, the lower bound stage, a collapse multiplier of 133.4 and an upper bound of 181. So you see a fairly good gap between these two bounds. You know the true solution is somewhere in between. You know the true bearing capacity is somewhere in between 133 and 181. That's already a useful piece of information that you wouldn't otherwise have, but that is in a way a standard part of OptumG2. If you look at the results, and you'll notice one thing here as well is that you don't have to go through a separate mesh generation stage. The mesh is generated behind the scenes as part of the analysis. So as a user, what you need to really pay attention to is the geometry, the materials, the features, load, supports and so on, and then you're ready to run the analysis. The mesh is created behind the scenes and the calculations are done. We can play sort of a movie of how this footing deforms. It's something like that. You'll see a slight movement to one side, and that's a perfectly natural consequence of the mesh being slightly unsymmetric. And if you look at real life, this is actually how these types of footings almost always fail, never straight down, but always to one side. You can see the plastic strains here. They are concentrated, of course, around the edge of the footing. Now, if I wanted the footing to move straight down, that might be due to constraints imposed by the building on top. I could use normal supports here. I'll try to do that in both cases. That wouldn't change the results. It would just change the kinematics of the collapse solution. But I have these two values, a lower bound of 133 and an upper bound of 181. And to improve on those results, I can do two things. I can increase the number of elements, or I can use mesh adaptivity. And how to use mesh adaptivity? Well, you say yes to that in both stages, and you see some settings here, some additional settings. First of all, the start elements 1000, and then 3 iterations. What that means is that you start with 1000 elements, just as shown here. Then you get a solution shown here, and then on the basis of that solution, you adapt the mesh. So basically, you refine the mesh in the parts of the problem domain where things are really going on. So in this case, it's in the colored area here where you have plastic straining, and then you coarsen the mesh where nothing is going on, say far away from the foundation. You do this once, then you get a new solution, and you do it a third time. That's the third iteration. So here we start with 1000 elements, and we end up with 1000 elements. So basically, in the course of 3 iterations, we are shuffling 1000 elements around to have the best possible solution. And let's see what happens. We start with the lower bound. We start at some 130 something and move up to 148, and the upper bound comes from above, from 181 down to 161. So now the gap has shrunk quite considerably. Again, we know the true solution is guaranteed to be somewhere in between the 148 and the 161. That might be something like 155, and so that would be a reasonable estimate of what actually the bearing capacity is. You can of course use even more elements and more adaptivity iterations to get an even more accurate solution, but with this error that we have now, we would somehow think in most cases that would probably be all right. To show you the adapted mesh, it's shown here, and that of course captures the solution. The slip lines you can see have become much more distinct now as a result of the mesh adaptivity. So so that was the bearing capacity. That's the first part of the problem. The second part of the problem, namely settlements, is we want to determine the settlements under the working loads. And if the limit load is, the ultimate limit load is 155, then a reasonable working load might be something like 100. And in order to do the settlement analysis, I again clone the stage, and then I want to change the load from multiplier, we are not multiplying anything, to being fixed at 100. And I don't want to do a limit analysis anymore. What I actually want to do is an elastoplastic analysis. So basically determine settlements. I'm again going to use 1,000 elements, and I'm again going to use mesh adaptivity. So mesh adaptivity is a feature that's available for all analysis types, and it not just limit analysis, and it improves the accuracy of any analysis that it's applied to. And in this case, you can see with the elastoplastic analysis, again, this is sort of how the footing moves. We plot the, let's plot the plastic strains again. You see, of course, they're much less developed, the plastic straining, than in the case of where we are at the ultimate limit state. So here we are somewhere before, well before the ultimate limit state, and the mesh, of course, that's reflected in the mesh as well. It's adapted not only to capture failure, but actually also to capture the elastic deformations you have in this problem. To get the results, let's plot the displacements, the vertical displacements. They're shown here, and again, if you want the exact magnitude, well, anything you see on the screen, you click it, and the results come up over here. The whole full result set actually comes up. The stresses and the displacements are down here, and you can read off the UX at the vertical displacement of about, in this case, 6 millimeters. If you're happy with those results, well, you're done. So you don't really need a full load displacement analysis from zero load to failure. But if you want it, and it might be nice to have, I kind of like to have it myself, then you can do that analysis as well. It's called multiplier elastoplastic analysis. You can think of it as a combination in a way between limit analysis and elastoplastic analysis. It takes the load from zero up to failure and calculates displacements, settlements, deformations at each load step. So we start down here from no load at all, then we have an initial almost elastic or in any case linear part. We come up to the working load was 100, and this is the part on the curve where things start to go from being linear to becoming more and more plastic. You lose stiffness basically. So that's probably where we want to be. So that analysis can be conducted as well, even though in many cases it's not strictly speaking necessary. You have the information you need from the two other analysis, the limit analysis and the elastoplastic analysis. And this was for a coarse mesh, I should say. You can of course use as many elements as you like, and you can use mesh adaptivity as well. So then I wanted to show you just briefly an example of a strength reduction analysis, which is, I think, the method of choice when it comes to slope stability. So I'll draw a slope, and again I won't worry too much about the exact dimensions, but draw something that represents a slope fairly well. Something like that. I'll apply material, and in this case I'll apply the default firm clay MC material. That's a more Coulomb material. It's one of the default materials. It's a more Coulomb material with parameters that you could say are representative of firm clay. You shouldn't take these two literally, of course, and you can edit the parameters if you like as well. So, but in this case, what matters to slope stability is the C and phi, and of course the unit weight gamma, and we will just stick with the default values: cohesion of 10, friction angle of 20, and unit weight of 20. Again, standard fixities is what we want to apply. And then the analysis type is strength reduction. I'll again use 1,000 elements. I'll use mesh adaptivity. And I have a lower bound stage now, element type lower. I clone the stage and have an upper bound stage. And I then run the analysis. And in strength reduction, you go through a sequence of iterations where you reduce, in this case with more Coulomb, it's C and tan phi you reduce. And the factor that you need to reduce these parameters by in order to cause collapse is then a measure of the factor of safety. So that's the strength reduction factor, or if you like, the factor of safety. So a lower bound of 1.34 and an upper bound of 1.37. So a very good, a fairly narrow gap between the upper and lower bounds. So that's information I think is safe to say that you don't get with your standard limit equilibrium programs. Be aware also that this is very, very different from limit equilibrium. Limit analysis and limit equilibrium are often kind of confused a bit, but it's two very different things. Limit analysis has really a rigorous theoretical foundation, which is what allows us to calculate rigorous upper and lower bounds. You see the adapted mesh. You see the slip line here, you see the deformations. Okay, so very simple to conduct this type of slope stability analysis. Now for the final problem, I wanted to do an excavation analysis, which is an example of a staged construction or staged excavation analysis. So the setup I'll consider is I have a soil domain, something is shown here. This soil domain is sand. I'll use the medium sand MC. It's a more Coulomb material again with a friction angle of 35 degrees and a cohesion of 0. Note it's actually 0, it's not 1.6 or 2.3 or whatever you need to get things to run. And standard fixity. So this would be our initial situation, and we want, say, to create an excavation that looks something like this, say. So we want to remove this material, and we know this being sand, of course, this is just going to come collapsing down immediately. So before we do the actual excavation, I'm going to ram down some walls, some sheet piles, and those can be modeled using the plate elements that we have available. The parameters of those, well, I mean, that's some plate parameters, EA, EI, yield moment, weight, and so forth. So this would be our initial situation, and it's for this initial situation that we want to, first of all, calculate. We need to do that, calculate the initial stresses before we start excavating. So that's done via the dedicated initial stress analysis, which basically determines a stress field that satisfies equilibrium and the failure criterion and so forth, and also makes sure that you comply with the earth pressure at rest conditions. So K0 in this case is 0.43, which in this case corresponds to the 1 minus sine phi relation, but it could be any number here, and the initial stress analysis then generates a stress field that complies with this earth pressure coefficient. So we want to, so this was our initial situation, and then we want to start excavating, and in order to do that, well, I clone the stage. And what is an excavation? Well, that's removal of material, and that's the way it is in real life, and that's the way it is in OptumG2 as well. So the second stage here, we want to calculate deformation, so it's an elastoplastic stage, and we want to start this stage, the first excavation stage, we want to start that from the previous stage, the initial stress stage. I clone again, I excavate some more, and again I need to start this stage from the previous one. It's again an elastoplastic stage, and let me do a third one. Let me take a big chunk off like that, and I know somehow that this would probably not be stable. So what I can do to stabilize things is put in a strut between the walls. That can be modeled using a so-called connector. It's basically a kind of a line element that is actually doesn't interact with the soil. It wouldn't have interacted with the soil in any case for this particular setup, but in general it doesn't interact with the soil, these connector elements. So that's useful for modeling struts. And then I'm ready to go. So I basically have the initial stress stage, first excavation, second excavation, third excavation stage with the addition of a strut. And let's see what happens. So then calculations proceed, and they're done now. Again, a fairly coarse mesh, and again you can use as many elements as you like, and you can then play a bit of a movie. Look at the deformations. Initially we have quite a bit of heave, and then as you go deeper, well, the walls start to cave into the excavation. That becomes a dominant mode of deformation, and as you go even deeper and you've inserted the strut, you have this mode of deformation. So that is how an excavation analysis works. There's no need to, as is usually done, define everything and then activate and deactivate various elements and structural elements and what have you. What you do is in an excavation is you remove material. And if I had wanted to do an embankment construction, well, then I could have added material. So that's how it works. There's examples, much more extensive examples of both excavation and embankment construction and various other stage construction examples, tunneling, for example, available in the manual. So that brings my presentation to a conclusion almost. I would just like to say that the program can be downloaded from our webpage, OptumG2.com. We provide trial licenses, free trial licenses, which give access to the full version of the program, no restrictions, for a period of a month. We have more permanent licenses, of course, as well. And we have, as an optional part of our licenses, we offer also support and maintenance contracts, which, of course, apart from support, also cover all updates, all bug fixes, and all new releases of the software. So that brings the seminar to a conclusion, and thanks for tuning in. We will have other seminars more on specific applications on OptumG2 starting shortly. So tune into those as well if you're able to. Thank you.